All right, so I got a request to try to explain J coupling. I think this is an organic one question. So to understand J coupling, we kind of have to take a look at. We're going to do a hypothetical here of just two hydrogen atoms. That off somehow. So we have hydrogen atom A bound to some carbon, and hydrogen atom B bound to another carbon. They can have two spin states, so they can have clockwise and counterclockwise. So unfortunately, when people teach in NMR, sometimes they try to teach this as, sorry, got my camera covered up here. So they try to teach this as spin up, spin down. That's not actually the right way to think about it. The way we think about it is that there's two stable ways a spin 1/2 nucleus can feel a magnetic field. Spinning clockwise and spinning counterclockwise align the magnetic field. So if we have hydrogen atom A and we have hydrogen atom B, hydrogen atom B can be spinning clockwise or it can be spinning counterclockwise. Because of these differences in rotation, we're going to see a change in energy. So if we just had the chemical shift, sorry, getting used to being back and bursting it. So if we look at the chemical shift of just hydrogen atom A, it has some baseline chemical shift. But this is actually going to get broken into two different signals. One, when hydrogen atom B is spinning clockwise, and one where hydrogen atom is spinning counterclockwise. Now, there's an equal chance that hydrogen atom B will be spinning both clockwise and counterclockwise, and so we expect there to be equal areas. So what's going to happen is that our signal for hydrogen A is going to get split into two peaks. One corresponding to hydrogen atom B spinning clockwise, one corresponding to spinning counterclockwise. But it still has the same baseline chemical shift between the two. So we will get what's called a doublet, a D. And so this doublet comes about from hydrogen atom A interacting with hydrogen atom B. Now, let's say we redraw our molecule again. So we have HA, HB, but now we've got two B atoms. We have two hydrogens sitting attached to the same atom. So the difference in this energy is called the J coupling constant. And if two hydrogen atoms are in the same environment and they couple with another atom, they're going to have the same coupling constant because it doesn't make sense to say these hydrogen atoms look any different. So now what ends up happening is we get our first split due to one of these atoms, and then we get a second split. So we actually end up getting a triplet. And the reason we're going to get a triplet is that there are three unique possibilities. We have one where, we'll do a table. We have one where atom A and hydrogen atom A and hydrogen atom B, hydrogen atom B, they're both counterclockwise. We can have a combination where one is counterclockwise, one is clockwise, one is clockwise, where one is counterclockwise. So basically, we have two combinations where we can have one spinning clockwise and counterclockwise, and we have one where they're both spinning clockwise. So we end up getting this 1 to 2 to 1 ratio in terms of probabilities. So we get a triplet, and the integrated areas are 1, 2, and 1. And we can keep up this pattern. Let's say that there are 3 B atoms. Well, this is going to split again, and this will give us a quartet. Now, this is just for this atom interacting with these 3. What happens if I introduce another atom here, HC? Well, unless that other hydrogen has the same coupling constant, what we're going to end up seeing is these peaks splitting up. So these peaks will split about with the J coupling constant associated with hydrogen atom C. So this is where the origin of our J coupling comes from. It has to do with the fact that atoms in hydrogen atoms, or 1H, particularly with hydrogen atoms, we see this the most, they end up interacting with the nuclei that are closest to them. And depending on their orientation, whether rotating clockwise or counterclockwise, it will actually change the energy associated with that chemical shift. Now, a few things to note on J coupling. So that's the theory. J coupling does give us some very important information. First thing it tells us is it tells us the number of adjacent hydrogens. So if we have a hydrogen atom, so let's say I have this molecule. So if I have hydrogen, we're going to designate A and hydrogen's B. What I expect, and we're just going to assume that for whatever reason there's no hydrogens here. Our J coupling is going to tell us the number of hydrogens that are on the adjacent carbons. So in this case, there's 0 here and there's 2 here. So this hydrogen, we expect to see a triplet in the pattern. And for these two, because they're adjacent to one hydrogen, we expect them to have a doublet. Now, if we had other hydrogens over here, we'd expect to see a triplet of something, or so if there was one hydrogen here, it would be a doublet of a triplet. If there were two, it would be a triplet of a triplet. If there were three, it would be a quartet of triplets. So the number of J coupling, the number of peaks we see is sorry, let me make sure I'm saying this correctly. So if we look at a pattern, the amount of splitting is 1 plus the number of hydrogen atoms. So if we have a doublet, we actually subtract 1 to figure out the number of adjacent hydrogens. So if we have a doublet, we have 1 adjacent hydrogen. If we have a triplet, we have 2 adjacent hydrogens. If we have a quartet, we have 3 adjacent hydrogens. Now this just assumes that those are the only ones that are interacting. If we have a doublet of triplets, it means that we have one hydrogen on adjacent carbon and 2 hydrogens on another. So that's the big thing J coupling tells you, is the number of adjacent hydrogens. That's really about all it can tell you, at least at level of theory we're going to. But as I talked about, and if you're in Organic 2, we do a review session this week. As I talked about in lab today, there are 3 pieces of information you can get off hydrogen NMR. One is an estimate for what the functional groups are. So that's where your chemical shift comes from. 2, the number of hydrogen, the relative ratio of hydrogen atoms in the molecule. So that's where your integrated area comes from. And then the J coupling gives you the number of adjacent hydrogen atoms to that particular functional group associated with that chemical shift. So if you have a doublet at a given chemical shift, it's adjacent to 1 hydrogen. If you have a triplet at a given chemical shift, those are adjacent to 2 hydrogens. Carbon-13 NMR, this is something that students kind of, sometimes they're just misinformed about, but honestly it's just practical. Carbon-13 does do J coupling, but the big thing is that when it comes to 1H NMR, the 1H isotope of hydrogen is 99% of the hydrogen atom, so it makes sense that they J couple. For carbon-13 nuclei can J couple just fine, but the problem is that there's a 1 in 100 chance that any given carbon atom is carbon-13. So it's not that carbon doesn't J couple, it's just that the carbon-13 NMR, the odds of 2 carbon-13 atoms being close enough to J couple is astronomically small. So practically, we just don't see J coupling in the carbon-13 NMR. So the only thing the carbon-13 NMR can tell us are the relative number of carbons and the number of functional groups, so the number of carbons in different functional groups. Now, other than that, I didn't really receive any other questions today. So, are there any questions out there of my one concurrent viewer? All right, so there's no questions. I'm at work, so I've got my guitar. Mostly indeed. So question that just got asked. So in the modeling homework, it gives you an example of a molecule that has 4 chiral centers, and it says the R's are referring to the symmetry at a given position in the molecule. So for each of the chiral centers, one of them is going to be R, one's going to be R, the other's going to be R, and the other's going to be R. So when it says the 4 R's, what it means is that all 4 chiral centers have R symmetry. So R symmetry means that if you use the Conic-World priority rules and you look at the molecule as the lowest priorities pointed back and the 3 highest priorities looking at you, if the priorities go counterclockwise, it's S symmetry. If they go counterclockwise, if they go counterclockwise, they're S symmetry. If they go clockwise, they're R symmetry. So for every chiral center, it can be either R or S. And so for every chiral center, there's 2 possibilities. So the number of potential diastereomers and enantiomers, or stereoisomers, is 2 to the number of chiral centers. So that's where your 16 comes from. Now, as far as picturing it, it's not really meant for you to draw. I built this molecule, and it's not worth it to build it. The bigger thing is getting you to understand how enantiomers and diastereomers work. So if you just have a molecule with 4 chiral centers and all are R symmetry, the enantiomer flips all the R's and S's. So for the 4 R's, the enantiomer is the SSSS configuration. Any diastereomer is going to be, diastereomers are any molecule. Diastereomers are related by at least one chiral center being different, but not all chiral centers being different. You don't even have to make up a model. This is just a hypothetical molecule with 4 chiral centers starting out with R symmetry. So you want to write out all the possible combinations of R and S and group the diastereomers and enantiomers. So engineers do pretty well with this because there's a really meticulous way to do it. So if you start with the 4 R's, the next diastereomer would be the SRRR, and its enantiomer would be RSSS. Next enantiomer, RSRR, its enantiomer is SRSS. Next diastereomer is SSRR, its enantiomer is RRSS, and you just start working through the pattern until you end up building all 16. But it's just a hypothetical molecule with 4 chiral centers. I think they give you that molecule, but again, we tried building it. There is no mesoform after building that stupid molecule. But just some hypothetical molecule with 4 chiral centers. And again, assume there's no mesoform. What meso will do is going to eliminate 1 pair of enantiomers. So you're going to subtract off -1 for each. No, that's not how it works. Divide by 2 and add 1, I think, something like that. Yeah, it gets really complicated when there's mesoforms of multiple with like 4 or 5 chiral centers. Glad I could help. Any other questions? Really wish I brought my tuner today. Oh well. Singleton. Ah, score. Yeah, you're out. That's right. There we go. Marx is skipped. I didn't attempt to. That's a good question. I've never had that issue before. Oh, it says skip because if you even view the problem, it just thinks that you tried it, but you can always go back and redo the problem. So if it's saying you skipped it, basically all that happened was you looked at it and just didn't answer any questions. Yeah, it's a weird feature in Connect that the problem's even viewed. It's considered as you starting the attempt, but I don't. Again, like there is no like forced time limits on the homework. So other questions you got for me, Hannah? All right. So, what, anything just general, or why we even bother with Frost circles? I mean, they are a weird theory in that they're not really a theory. So, Frost circles are more a way to explain the 4n+2 rule. We don't practically use them for any type of analysis of organic molecules. And the reason being is that Frost circles are kind of this weird child of molecular orbital theory and Lewis theory, and those two theories should never have children. So for organic chemistry is based in Lewis theory, which predates quantum theory. So Lewis theory actually began to show up about 10, 15 years before Schrodinger's wave equation, all of that showed up. So it didn't even assume SPDF orbitals. Now, molecular orbital theory showed up after the quantum era showed up. So once we had SPDF orbitals, molecular orbital theory showed up. And molecular orbital theory says that molecular orbitals are created by taking atomic orbitals, your SPDF orbitals, and adding and subtracting them. So this theory, molecular orbital theory, is the more complete theory, and it makes predictions that aren't seen by Lewis theory. The big thing being bonding, anti-bonding, and non-bonding orbitals. So if you look at Lewis theory, so if you look at Lewis theory, and we have two hydrogen atoms. Well, we draw an electron, and we combine the two of them, and we say we formed a bond. But there's nothing in here that really, one, predicts that there's anything other than just this bond. And it also doesn't tell you anything about the shape of that bond. It just says that there is a bond. So that's Lewis theory. Molecular orbital theory says, well, actually, each hydrogen atom contains a 1s orbital. And each 1s orbital contains one electron. So we're going to add the wave functions together. So your s orbitals look like spheres. When we add them together, we're going to get kind of this long eclair-shaped orbital. This is our bonding orbital. And then if we subtract them, we're going to get kind of this p-shaped orbital, where there's a gap in electron density between the two. And this is our anti-bonding orbital. And this is the correct picture for hydrogen. So hydrogen, our two s electrons, go down into the newly formed molecular orbital here, and there's an anti-bonding orbital here. Now, for hydrogen, this is easy to do because we only have a 1s orbital. If we go to something like water, though, oxygen has the 1s, the 2s, and the 3p orbitals. So even for very simple molecules, molecular orbital theory gets really complicated. But the big thing here is that molecular orbital theory makes two predictions Lewis theory can't. One, it predicts the shape of the orbital, so we can see where the electron density is. And two, it predicts the presence of these anti-bonding orbitals. Now, if we go to something like benzene. So we got carbon, 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 hydrogen, 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 hydrogen. And we draw in all the bonds by Lewis theory, we get this. Well, this isn't the complete picture for benzene. There's antibonding orbitals that don't show up anywhere in this diagram. There are non-bonding orbitals that don't show up anywhere in this diagram. So Frost diagrams were meant to draw a compromise between the fact that Lewis theory gives us a really simple picture, but it's missing a lot of details. And something like molecular orbital theory, you've got 6 carbons, so you have 6 1s orbitals, 6 2s orbitals, 18 2p orbitals, and each of the hydrogen orbital 1s orbitals. This is why the theory gets really complicated, is that molecular orbital theory can't be simplified. But we're going to try to simplify it to accommodate Lewis theory, which was never designed to account for it. So this is where the Frost circle comes in. And it says that, okay, really if we wanted to do this right, we'd have to use all the atomic orbitals. But we can't because it is impractical to do molecular orbital theory by hand this way. So we're only going to concern ourselves with the orbitals that are used to make the double bonds. It's a terrible approximation, but it's what we're going to do. So we're just going to ignore all the orbitals that were used to make what are called the sigma bonds, which are the first bonds between the carbons and hydrogens. So we got our carbons. The first bond formed between any atom in Lewis theory is a sigma bond. So if we only look, if we draw in all the bonds that are formed due to sigma bonding, we're left with an unpaired electron on each carbon. So this unpaired electron we're going to claim is coming from a p orbital. So now we're going to do molecular orbital theory on just those p orbitals. And molecular orbital theory has a rule that says that for every atomic orbital you use, you should end up with 1 molecular orbital. So if we have 6 atomic orbitals here, each containing 1 electron, we have to finish with 6 molecular orbitals. On top of that, we know that we're going to have bonding and anti-bonding and possibly non-bonding. So to approximate this, what we're going to do is we're just going to draw a circle. And we're going to split the circle technically into 3 parts. We've got the bonding, the anti-bonding, and across the center is the non-bonding. Now, we know that we're going to have 6 molecular orbitals. We know that 1 has to be a bonding orbital. So we're going to draw 6 orbitals, 6 molecular orbitals. We don't care about the shapes. We don't care about their energy so much. We just care whether or not they finish above or below this line or at this line. And they're all going to be equally spaced. So we're going to draw a hexagram. 2. So these 3 lines are molecular orbitals that we're probably generating with those p orbitals. Now, each of those atomic orbitals on those carbons had an electron in it. So now we need to add 6 electrons to the diagram. So we have 1, 2, 3, 4, 5, 6. So the Frost diagram says that if we were to go through and really grind through the molecular orbital theory, regarding the electrons in the pi bonds or the lone pairs or anything we're using to generate the aromatic system, all those electrons here are going to sit in bonding orbitals. None are in non-bonding. Now, if we had 8 electrons, we would finish up with 2 electrons in non-bonding orbitals, or anti-bonding orbitals in this case. So if we finish with any electrons in any non-bonding or anti-bonding, it's not aromatic. And the reason being is that if they're non-bonding, they're not participating in anything. They're basically sitting in atomic orbitals. There's no reason to form a bond. And if they're sitting in anti-bonding orbitals, they're not mobile because typically anti-bonding orbitals have a lot of planes in them. They have a lot of regions of 0 electron density, so they're not very mobile. So if you do this enough times, what you pick up on is that if you have 4 n plus 2 electrons in your aromatic system, they will always finish in the bonding part of the Frost circle. If you have 4N, then you will either finish with non-bonding or you'll finish up with anti-bonding. So you'll end up with an anti-aromatic compound. So the Frost circle is this really oversimplified approach to understanding the molecular orbitals that come out of an aromatic system. Each of these lines represents an orbital we use to build the aromatic conjugated system. Usually they're just p orbitals. And each electron represents one of the electrons in the aromatic network. Again, this is not particularly useful for much other than proving the 4n plus 2 rule, just because if you do this enough, you'll pick up on that. You'll start seeing this pattern. But as far as other information, it can't give you any other information because true molecular orbital theory is going to require you to figure out the symmetry of those orbitals that you're creating, and there's rules. You can have one S type, you can have up to 3 P types, up to 5 D types, and so forth. But that's the real picture, and it's hard to do by hand. And the notes do go through like what you end up getting. But the notes are more meant to illustrate that this is an oversimplification of a very complicated idea. Ultimately, it's just that 4n plus 2. Yeah, that's really the problem, is that you can't, with molecular orbital theory, you can't cut corners. You have to do the full theory. You have to count for every orbital, and you have to worry about symmetry. There's a lot that goes into it. In fact, your first test in inorganic chemistry is group theory. You learn a special subset of mathematics so you can start predicting symmetries. None of that's showing up in any of this discussion. So you don't have enough information to really do molecular orbital theory. And Lewis theory doesn't predict any of this. Like, it doesn't predict antibonding orbitals. It doesn't predict aromaticity. It doesn't, like, none of it. And so you kind of got one theory that's not good enough, another theory that you oversimplified, and now you've slapped them together to create a weird hybrid of theories that doesn't really address anything other than why the number of electrons matter. So I teach Frost circles because they're in the book, and I'm sure there's some organic chemist right now who's screaming because I'm saying Frost circles really aren't that relevant. But that's my view on Frost circles. They're kind of, you never see them. They're not that useful. They're cute from a standpoint of explaining what anti-aromatic compounds are, but so much information is missing from them. Now, that said, I wonder if I have my inorganic chemistry book here. Yeah, I do. In the defense of the organic chemists, I will say molecular orbital theory is hard. See if I can find you a molecular orbital diagram. Come on, I know you got carbon monoxide in here somewhere. Here you are. So this is the molecular orbital energy diagram for carbon monoxide. So just C and O, you end up with a picture that looks like this. So all these energy diagrams, these are all the molecular orbital shapes. So yes, to their credit, molecular orbital theory is incredibly hard to work with by hand. That said, it is the more complete theory. And it does predict all these things. But you can't do molecular orbital theory by hand, except for very trivial examples. All right, so we're coming to the end of the stream. If you've got any questions, again, feel free to email me. We have a live stream tomorrow at 10 a.m. and then the last live stream of the week is going to be Friday at 2:30. Thanks to everyone who was able to show up, and I will see you all tomorrow.